Okay, thank you very much for the invitation. So I'm going to talk about some quite recent, it's 1 year ago maybe, paper that we wrote with Leo Tzu and Marco Mazzucchelli. And it's a rigidity result in the spirit of boundary rigidity, but except that that's for non-compact spaces. So let me start. Oops. So let me start with conjugate point because that's one of the topic of the paper and the talk. So by the way, there is the article is on the archive if you are interested. So for conjugate point, what are conjugate point? So if we fix, you have to take a complete Riemannian manifold. And we said that 2 points are conjugate if between the 2 points there is a geodesic joining them. So I call it gamma of t. And the endpoints are given by x and x prime. So gamma 0 is x, gamma of 1 is x prime. And there is a Jacobi vector field, which I will denote by z. So it's just a vector field defined along the geodesic, which vanish at the 2 endpoints. What are Jacobi fields? Jacobi fields are a solution of some ODE involving the curvature tensor. So I wrote the ODE, it's a second order ODE. And the one way to construct a Jacobi field is to take a variation of a family of geodesic. So there is an alternative definition which is more related to symplectic geometry, and this is the one maybe we better use in microlocal analysis, which can be described in terms of the differential of the geodesic flow. So the geodesic flow, you can view it as a flow of a vector field acting on S of m. So what is S of m? It's the unit tangent bundle. So the sphere, the bundle of spheres inside the tangent bundle, and the spheres are defined using the metric G. And I will denote by pi the base projection. So when you have a fibration like this, you can define a vertical bundle. Vertical bundle is just the kernel of the differential of pi. So fibers in the vertical bundle are just tangent to the spheres. And we said that, equivalently to what I defined before, it can be proved that x and x prime are conjugate if, well, again, x and x prime are joined, or can be joined by geodesic. So v is the tangent vector at x pointing toward the geodesic x prime, and v prime is the tangent vector of the geodesic arriving at x prime. And there exists a non-zero vertical vector such that if you look at the differential of the geodesic flow phi at time t0, it will bring this vertical vector to another vertical vector. So you can say it's when you look at the action of the differential of the geodesic flow, it takes the vertical bundle. When you evolve, it becomes straight away non-vertical, but it's possible that after some time it comes back vertical. And this is exactly when we have a conjugate point. So one property of conjugate point, which is used a lot, is that when you have no conjugate point, for any pair of points, x and x prime, you can you get a unique geodesic joining x and x prime, at least assuming that M is a simply connected manifold. If it's not simply connected, then you have a unique such geodesic in each homotopy class. And another way also to describe it is in terms of the exponential map. So the exponential map would be diffeomorphism in that case where M is simply connected. So now that I defined the conjugate point, so first, one remark that I didn't write, but which is important about conjugate point. The typical example of manifold with no conjugate point is the case where the curvature is non-positive. So when you have non-positive sectional curvature, it's easy to check that there is no conjugate point. But there are manifolds with no conjugate point which have a little bit of positive curvature. So it's a more general class. And this class has been studied quite a lot since maybe 60 or 70 years ago. And it's not very easy to say stuff about them, like classify and so on. So it's always interesting to get some sort of classification or rigidity result for such manifold. Now I will come to my the class of metric that we have considered. So we call them asymptotically Euclidean. Basically, they are perturbation of Euclidean space, of the flat Euclidean metric. And at least the class I will consider is as follows. So I take Riemannian metric G, smooth, everything will be smooth always. And I will say that it's asymptotically Euclidean to order M. So M is in the paper and in the talk is going to be an integer. We could also work with non-integer, but for simplicity, we took M to be integer. And the metric we assume G is of the form G0, where G0 is just the flat Euclidean metric, plus a perturbation. And we assume that the perturbation can be written under the form I wrote. So it's a matrix, symmetric matrix, which decay to order 1 over x to the power m at infinity when x go to infinity, and which has an expansion, an expansion in homogeneous powers of negative power of modulus of x at infinity. So in fact, in the result, we don't need a full expansion. We just need an expansion to certain order. But to simplify, and we have just assumed that G has really a full expansion at infinity. So here is the result that we proved. So we show that if you take an asymptotically Euclidean metric on Rn, and you assume it's asymptotically Euclidean to order m bigger or equal to 3, if this metric has no conjugate point, then it must be isometric to the Euclidean metric. So it must be flat. So it's a kind of rigidity. It means you cannot have a metric which look like Euclidean space near infinity and which have no conjugate point. So anytime you do a perturbation of Euclidean space, if at infinity it's a small perturbation, then it means that you must create conjugate point. So as a remark, as I said, for the result, we just need a finite expansion in power of x to the -1. And the number of power we need depend on the dimension, basically. Another remark is the m here is bigger or equal to 3. So it means it's really short range perturbation of Euclidean space. It's not so clear. We tried quite a bit to go down to m equal 1, but we couldn't really figure out. So it's an open question if someone finds an idea how to improve it. I believe it should be true also with m equal 1. But, anyway. And another remark is that it's kind of sharp in some way, in the sense that it's not very hard to construct metrics on Rn, which look like asymptotically like some cones near infinity. So when you write in polar coordinate, it can be written as d r square plus f of r squared d theta squared. So they are warp product metric. And you take f of r equal a times r for some a strictly bigger than 1 for r large. And you can actually construct them so that G has non-positive curvature. So then if you have non-positive curvature, it means you have no conjugate point. So they really look like cones, but the angle of the cone is slightly more open than Euclidean space. For Euclidean space, A would be 1. So it means that really the Euclidean infinity in this type of rigidity result is really a kind of boundary, a kind of transition case. So there were some results already known on that problem. The first result we could find was by Green and Gulliver, and then by Crook in 1990. So Green Gulliver was in dimension 2, was for the plane, and Crook was for any dimension. And they were considering compact perturbation of Euclidean metric. So they were showing that if you have a compact perturbation of Euclidean metric with no conjugate point, then it must be flat. So when we started to look at this question with Leo and Marco, the idea was to see up to what kind of perturbation this type of result can be extended. So we consider this class of metric. There were also some results by Inami in '86. But this result involve, I mean, they have some global assumption on the curvature. While here in our assumption is just an assumption about things at infinity, like the structure at infinity, that it's really asymptotic to Euclidean space at infinity. But in the compact, in any compact region, we don't really assume anything except no conjugate point. While in the paper of Inami, he assumed that there is some, like the Ricci curvature is integrable. So of course you can say it's something also about infinity in some sense, but also some identity on the integral of the scalar curvature. The scalar curvature needs to be integrable, and the integral needs to be 0 for the result to hold in any. So the class we consider does not really enter in any result. It's also related to, actually, in the result of Crook and Green Gulliver, they're really related to the question about boundary rigidity, which in this class was analyzed by René Michel and Gromov. So they show basically that a metric with no conjugate point with the same boundary distance as the Euclidean space on a strictly convex ball in Rn has to be flat. And indeed, Crook really reduced, in his proof, reduced the problem to the boundary rigidity when you compare a simple metric G with the flat metric. And another relation is the case of a closed manifold. So manifold with no conjugate point have been studied quite a lot also in the closed case. There was a famous conjecture of Hopf, which was proved in dimension 2 by Hopf, which said that if you have a metric on the flat, so if you have a metric on the torus, if it has no conjugate point, then it must be flat. So Hopf proved it for dimension 2, and Burago-Ivanov in a famous paper proved it later in any dimension, much later actually. So there are also some other results for a cylinder of this type by Burns and Knipper, for instance. So let me come to the ideas of how to approach this problem. So the first thing is to find good coordinate near infinity. So what we can do is to find a sort of radial coordinate adapted to the metric G. And the way I want to formulate it is that there exists a diffeomorphism from the cylinder, the half-line times the n-1 sphere, to the Euclidean space minus a compact set, which pull back our metric, our asymptotically Euclidean metric, to a metric which look like Euclidean space. So it's d r square plus r square times some family of metric on the sphere, depending on the coordinate r, the radial coordinate. And this H of R, we can view it as a family of metric depending on this parameter R, which has an asymptotic expansion as R goes to plus infinity. So at first order, it's given by the canonical metric on the sphere, plus a full expansion in power of R. And here you have H of J, or just tensors, symmetric to tensors on the sphere. So for convenience, we like to view the problem in terms of a compactification. It's not really necessary, but it simplifies quite a bit, because having a full expansion at infinity, if you compactify the problem, you can translate it into smoothness on the compact manifold with boundary, which is a bit convenient. Then you work with smooth function. It's easy to do analysis on them. So we will denote rho. Rho will be basically 1 over R. Okay, so when R go to infinity, you go to infinity over space, rho goes to 0. And we compactify Rn by just adding a sphere at infinity. So it's really a radial compactification at rho equals 0, which is equivalent to R equal infinity. So then the structure of the metric, which I wrote in terms of dr square, transfers to the form d rho square over rho to the 4. It's just dr square here, written in terms of rho. And then an expansion in terms of positive power of rho, increasing power of rho. Let me come to the scattering map. So it's not here because it's a talk in inverse problem. I know that many of you are familiar with quantum scattering and the scattering operator associated to wave equation or the Laplace equation. Here, we're not going to consider this, but we are going to look at classical scattering, because we're just looking at a problem on geodesics, so transport equation. So the structure of the scattering map is a bit simpler than the quantum case. And it's possible to define it as follows, using the asymptotic structure of the metric G. So if you take a complete geodesic gamma, you can prove that if you flow it forward and backward, you will converge to a point, which I denote by y plus or y minus, depending on if I go in the future or in the past along the geodesic. And it's a point on the sphere, which I view as the boundary at infinity of Rn. So it's just given by the direction. The point is given by the direction the line is going, to which the line is going. And then there will be a covector, which I denote by eta plus or minus, which is in the cotangent space to the sphere at y plus or y minus. And they are defined as follow. So you look at the geodesic gamma, you look at its tangent vector gamma dot, you contract with the metric to really get a covector, and you look at the limit, and you write it in terms of this rho and theta coordinate. Theta actually become y in my talk. So if you look at it, you can see that in the compactification, it's going to converge to a point y plus or y minus, depending on if I go to in the future or in the past on the sphere at infinity. And the tangent vector contracted with the metric, gamma dot flat, is going to be basically d rho over rho square is just minus dr. So it's just the dr is the radial vector field, the radial direction, plus this element eta plus or minus, which you can view as a cotangent vector to the sphere. So this pair y plus and eta plus or y minus and eta minus are cotangent vector on the sphere. So I will call this y plus, y minus, eta plus, eta minus, these pairs, as the past and future asymptotic vectors of gamma. Okay. So now it's also using the structure. So to prove this, you really have to look at the geodesic flow equation and use the fact that your metric looks a bit like Euclidean space at near infinity. And it's also not very hard. I mean, it's a bit of analysis, of course, but it's not so hard to prove that there exists also two Euclidean geodesic, which I denote by gamma 0 plus and gamma 0 minus, such that in the future, my G geodesic gamma of t is approaching gamma 0 plus of t. So it's approaching just a Euclidean line in the future. And same in the past, there is another one which is gamma 0 minus t, whose distance converge to when t go to minus infinity to my geodesic gamma t. And at the same time, if I look at the direction gamma dot of t, it's actually also converging to gamma 0 dot plus or minus t, which is just a constant in this case. So let me show you the picture. So here you see on the picture, I have my gamma of t. So I draw the compactification of Rn. So gamma of t is this geodesic for G. So in the future, it's approaching a point y plus, which is really given by the direction, the asymptotic direction of my geodesic. In the past, it's going to approach y minus. And it's going to be approximated by this, in the past, by this gamma 0 minus geodesic, which is a geodesic for the Euclidean space. And in the future, by this gamma 0 plus geodesic. So it's the same thing as, of course, in quantum scattering, you approximate the solution of the wave or wave equation using the free equation in the future and in the past. So let me come back. Just an example, if you take just the Euclidean metric and you take the Euclidean lines, which are just given by one direction. So eta is a fixed element in Rn minus 1. So it's just a vector like this. And then you take a line perpendicular to it. Then you're going to approach at minus infinity, you're going to approach the direction 0, 0, 0, minus 1 on the sphere. And with the covector eta given by this eta here. And the future is going to be 0, 0, 1 minus eta. So a simple exercise to do. So now, if you fix any covector on the sphere, which I will denote y minus eta minus, then it's easy to see that there is actually a unique Euclidean line, which I'll denote by gamma 0 minus, so that the limit of gamma 0 minus t and gamma 0 dot minus t contracted with the metric is going to converge to this y minus 0 over rho square plus eta minus. So basically, if you fix an asymptotic vector in the past, you get a unique Euclidean line, a Euclidean geodesic, which in the past will converge to this asymptotic vector. Conversely to the lemma I wrote before, so remember in the lemma before, I said that if I take my gamma geodesic for the metric G, there are two geodesic for the Euclidean space which approximate, one in the future and one in the past. Okay. So conversely, if now I take a Euclidean line gamma 0 minus, for instance, could be the one I had just before, then I can also show that there is a unique G geodesic which is asymptotic in the past to this gamma 0 minus. So it's the converse result to the one I had in my lemma. In my lemma, I have gamma of t, I approximate by a Euclidean line. Conversely, if I take a Euclidean line, I can actually approximate it by a G geodesic in the past. And same thing is in the future. So the conclusion of this is that if I fix any y minus eta minus cotangent vector on the sphere, an asymptotic vector in the past, then because I can first find a Euclidean line which is asymptotic in the past to this, and then in a second step I can find a G geodesic which is asymptotic to my Euclidean line, then in fact it shows that there is a unique G geodesic gamma which is asymptotic in the past to my covector y minus eta minus. So it's nice, it said that for any covector I can associate a unique gamma geodesic to it. So how do we define the scattering map? Well, first we take covector y minus eta minus, which I view as an asymptotic vector in the past. I take my G geodesic, which is asymptotic to it in the past. And then I look at its future asymptotic vector, y plus eta plus. So it defines me a map, S of G, which take the cotangent to the sphere, to the cotangent to the sphere. It can be shown that it's a symplectic map, actually. So usually in the field, people call it the scattering correlation also. But we can also view it as a map in that case. So now it's a little reformulation, a little exercise, which is not very hard, but not completely trivial either. I mean, it needs a bit of analysis, which is that how to characterize the fact that a metric G has the same scattering map as the Euclidean metric. So having the same scattering map as the Euclidean metric can be reformulated as follows. It's true if for all G geodesic gamma of t, there exists a Euclidean line, gamma 0 t equal x plus tv, such that gamma of t approximate gamma 0 of t in the past. So the distance between gamma t and gamma 0 t is going to 0 in the past. The tangent vector of gamma of t is also approximating the tangent vector of gamma 0, which is v. So it means that gamma and gamma 0 are really asymptotic in the past. And in the future, gamma of t is asymptotic also to gamma 0, but up to maybe a reparameterization. So there is a T0 appearing here. But basically it's saying that one has the same scattering map. If I come back to my picture, it says that the gamma 0 minus and the gamma 0 plus are the same line. So let me show on a picture. Here is a picture. You see, I have gamma 0, the Euclidean line, joining y minus to y plus, the 2 point at infinity in the compactification. And I need to have the same scattering that gamma of t is really, the distance is going to 0 in the past toward this line, and in the future also. But there is possibly a time delay. Oops, sorry. So the first reduction in our proof is to transfer the fact that a metric has no conjugate point and is asymptotically Euclidean to something about the scattering map. So here is what we show. We show that if you have an asymptotically Euclidean metric G on Rn, and you assume it has no conjugate point, then it must have the same scattering map as the Euclidean metric. So how to prove this? So that's the first step of the proof. Then we will use the fact that having the same scattering map tells us something about the metric. So for this, we use the idea which is in the paper of Krook. Remember I said Krook proved the same result as what we did, but for compact perturbation. But we apply it to our case. So it's roughly the same type of argument as Krook, except that because we are not in a compact perturbation case, there are a lot of quantitative estimate to do. So at first step, we thought this would not be too tricky, but actually it turns out to involve quite a bit of work. It's not completely trivial. And essentially what we need is really a full understanding, a full analysis of the structure of the geodesic flow at near infinity. So let me explain a bit the idea of proof, which is based on Krook's argument. So I will do the case where G equals G0 outside the compact set. So G0, remember, is the Euclidean metric. So I take a Euclidean geodesic gamma 0 of t, which cross this perturbation here. So the gamma geodesic is, when it enters the perturbation, it's distorted, then it starts to change. It's not anymore a Euclidean line, and then it goes out of the perturbation and becomes a Euclidean line again. So the first step is to show that when you come back from the perturbation, your Euclidean line is going actually to be parallel to gamma 0. It cannot be, the direction cannot be different from that of gamma 0, which really means that the endpoint at infinity is going to be the same. So remember on my picture here, to have the same scattering, we need to get the same endpoint for gamma of t than the Euclidean geodesic gamma 0. So here, it really means that this gamma of t has to be parallel to gamma 0. Because being parallel means that you're tending to the same point y at infinity on the sphere. And basically the covector eta measure more or less the distance, the Euclidean distance between these two parallel lines. So if G is equal to G0 outside the compact set, like on my picture, the idea is to do as follows. So you consider, you take a very large T, big T, and you look at gamma 0 of minus T, this last point on the left. And then you consider gamma of plus T, which is the one on the right. And you let big T go to infinity. What you can see is that what is not very hard to check is that if you look at this Euclidean geodesic, zeta index big T of small t, which is this Euclidean line, when big T is really large, this Euclidean line is not going to intersect this perturbation, G equals G0. And then it's going to be a minimizing geodesic between these 2 points. So then essentially what you will have is that you will have 2 geodesic joining these 2 points, and then this contradicts the fact that you have no conjugate point. So it really says that one cannot go back from the perturbation and not be parallel to gamma 0 of t. Because of course, if you're parallel, you cannot do this argument anymore. You cannot construct this zeta big T Euclidean line. So the argument is simple. Now we need to adapt it to the fact that we are not in a compact perturbation case, but we are really in a short range perturbation case. So we need to really estimate everything, and you see the idea in the end work, but demands quite a bit of estimate. Now the second step is to prove, we have proved that the endpoint on the sphere at infinity is the same as on my picture. So the G geodesic is distorted in contrast to the Euclidean line. And then there is a distance between, then of course gamma of t is going to be a Euclidean line if I were in a case where I'm in a compact perturbation. And they're separated by a distance a. And to prove that I have the same scattering, I need to show that this a is 0 actually. So I really need to prove that when I come back from my perturbation, I'm again on the Euclidean line. So this part is a little bit more tricky. I don't really want to go into detail, but the idea is to take a parallel line to gamma 0 of t, which is far from the obstacle, from the perturbation. And I want to take I want to take point again as before, which are going very far to infinity. And what can be showed using things like triangular inequalities and a bit of Euclidean geometry is that you can compute the square of A, you can bound it by the Euclidean distance between this far left point on the Euclidean line gamma 0 minus t. Oh, actually there is a square here, I forgot the square. So it's dg0 gamma 0 minus of minus t to gamma of t. Gamma of t is this point on the geodesic gamma, but far in the future, minus the distance the same distance, but with respect to the metric G. So this actually is an exact inequality in the case of a compact perturbation. Now, if you're not in the case of a compact perturbation, but more like a short range perturbation as in our case, roughly speaking, we use similar type of ideas and the fact that we can really estimate the geodesic near infinity to say that the same holds modulo some errors, and the error is the big O of t to the minus m plus 1, where m is the order to which our metric is asymptotic to Euclidean metric. So of course, what we want is to prove that A is 0. So basically, to prove that A is 0, we would need to show that the Euclidean distance between these two far points is less than the G distance. Then the right-hand side will be negative or 0, and this will show that A is 0. So that's the idea. To show this, we can do as follows. So here again, we use argument, similar argument that in Krog's paper. If you take 2 points, x and y, which have a geodesic crossing our obstacle, you can again take a parallel line far not containing the obstacle and consider this zeta minus t and zeta plus t, where t is large again. And you let them move to infinity. It's again a play with triangular inequality and stuff like that to show that actually here is really Euclidean geometry. You can show that the Euclidean distance between x and y is given by the limit between the Euclidean distance between zeta of t and zeta minus t, this long line on the bottom, minus the distance between x and zeta minus t, and the distance between y and zeta t. So of course, if we are in a compact perturbation of Rn, the metric G is just perturbed in the ball here. Outside is just Euclidean. So you see that this equality I wrote is just Euclidean geometry. And then, because G is equal to the Euclidean metric outside the ball, we can replace the Euclidean distance by the G distance. Here again, I'm doing just the case where G is G0 outside the compact set. So you get an equality again. It's the limit between the distance between zeta t, for the distance for G, zeta t, zeta minus t, and the distance between zeta minus t and x, and the distance between zeta of t and y. And then you can use the triangular inequality. Here, what you see is that you obtain the distance, the G distance between x and y. Okay, because the G distance between the bottom left point and the bottom right point is less than the distance between zeta minus t to x, and distance for G between x and y, and then the distance from y to zeta of t. But of course, because this is independent of t, it's just equal to the distance between x and y. So it tells you that the G distance is always more than the Euclidean distance. And if I come back to my previous inequality, it gives what I want. I get a squared is negative or 0, which means that a is 0. So it's a very, it's really a simple argument, quite straightforward and quite clever. That was done by Chris Krog. And here, basically for this part, we really have to follow this argument, and because our metric is not Euclidean, you need to control everything. You know? It's a little bit painful to do, but that works. And we get errors which depend on large t, and when t goes to infinity, the error goes to 0. So this shows that the scattering map of G is the same as the scattering of the Euclidean space. Okay, so now the second step is to get a volume estimate and volume comparison. So what we show is that if you have an asymptotically Euclidean metric with no conjugate point, as I said, it has the same scattering map as the Euclidean space. And then we can show that for each x0, each point, if you look at the volume of the ball for G of radius big R centered at x0, and you compare it to the Euclidean volume. Oh, actually, sorry, there's a typo here. It's the volume for G0. So it's just the Euclidean volume. So you compare the volume for G of the G ball of radius R with the Euclidean ball of radius R. Then the error between the two is given by a big O of R to the dimension minus m plus 1, where m is the decay, is the order to which our metric is asymptotic to Euclidean space. So how to prove that? Basically, the fact that we have the same scattering map, and in fact, in our proof, we also show that there is the same time delay. Time delay was this T0 that I defined before when I compare the future asymptotic Euclidean geodesic and the past. You can actually show that there is a conjugation between the two geodesic flow, the geodesic flow of G and the geodesic flow of the Euclidean space. So there is a map theta conjugation, which sends S, the unit tangent bundle of Rn with respect to the metric G to the unit tangent bundle of Rn with respect to the G0 metric. So the usual tangent bundle on Rn, and which conjugate the two geodesic flow. Moreover, this conjugation is going to be asymptotic to the identity near infinity. So if you remove a large ball of radius R and you let R go to infinity, the C1 norm of theta minus the identity is going to be small. And the smallness is described by the order to which we approach, to which the metric is asymptotic to Euclidean space. And then one can use some sort of Santalo type identity or something where you compute the volume, some volume in terms of disintegration along geodesics. And using this, essentially, you arrive to that estimate. So you see that, for instance, if M is very large, it means that the volume of large ball for the G metric is extremely close to the volume of large ball for G0. So now let me do a little digression. Because this volume estimate, they also come in a problem which is related to this rigidity. Crook in 92 proved that if you take the universal cover of a closed manifold without conjugate point, the volume of the G ball of radius R in the universal cover divided by the Euclidean volume of a ball of radius R, its infimum limit is bigger or equal to 1, and it's equal to 1 if and only if G is flat. So it's a sort of volume comparison, and a little bit like Gromov style, which characterize again the property to be flat in terms of volume estimate for manifold with no conjugate point. So this result was also proven for metric on the plane in R2 by Bangert and Emrich much more recently. But this similar problem is open in higher dimension if you're not on the universal cover of a closed manifold, but let's say on Rn, for instance. So it's a conjecture to see if the limit inf of the volume of large ball for G divided by the volume of large ball for G0 is bigger or equal to 1 with equality if and only if G is flat. It's not known in dimension more equal to 3. So there are a few papers of Crook and Kleiner on that kind, but they don't really solve this so generally. So now let me come to the rigidity, assuming first that M is large. So remember in my main theorem, I was assuming that M is bigger or equal to 3. So first we will show that our metric is Euclidean if it has no conjugate point, assuming that M is large. And when I say large, is large with some M depending on the dimension. So for this, we take a cylinder. So we write the coordinate in Rn as x bar xn. So xn is the last coordinate in Rn. And we take xn to be less than r in modulus and x bar to be less than r. So it's really a big cylinder like this. So I will show you the picture. That's this f of R0, sorry. So it's just a Euclidean cylinder. So x bar is in Rn minus 1, xn is in R. And you see that it's foliated by horizontal geodesic. And now define f of R to be the image. So because FR0 is a cylinder in Rn, but it's foliated by geodesic. So you can really view it as also as a subset of the unit tangent bundle by just taking the d over dxn direction. I view it as foliated with horizontal geodesic. So if I take the image with my conjugation, I will get, and then I project backward to Rn, I will get another kind of cylinder made of geodesic for G. You see on the picture. So it's kind of deformed and it's foliated by G geodesic. So basically what happens is you take each Euclidean geodesic, you take the image by our conjugation and give you another geodesic for G. And then we take this set. So just as before, I said that the volume of large ball for G and for G0 is kind of asymptotic. At least the difference is given by some power of R, which depend on M, on how close we are to a Euclidean space near infinity. So here, the same actually hold for this cylinder. So I did it with balls first, but in fact, it's also true with this large cylinder with the same type of argument. So here is the picture. So now, yeah, I just want to show you in terms of the compactification Rn bar, the geodesic foliating off of R, they correspond to geodesic with, because we have assumed, because we have proved that the scattering map for Euclidean space and for G are the same. Our G geodesic passing through this cylinder, when we flow them forward and backward to infinity, they will actually approach what I call the north and south pole. For Gunther, the north is on the left this time, and the south on the right. And you see in the compactification, the geodesic foliating are drawn like this, like a kind of football. And F of R is just this this region that I draw here in the middle. So what you can see is that in terms of this y eta coordinate that are describing asymptotic endpoint, all these geodesic, if you look at their backward endpoint or forward endpoint also, they correspond to y equal the north pole, at least when you look at backward, what I call the north pole. So it's the one on the left, the infinity on the left. And the covector eta, there will basically be a ball. Eta will be less or equal to R. So then, remember, I said that we can compare the volume of this cylinder for the metric G with respect to the Euclidean volume. And they are equal up to some big O of some power of R depending on M. And when M is large, this thing, when R go to infinity, is going to 0. So now I want to estimate this volume also in another way. So I want to write this volume. I want to disintegrate it using this coordinate given by the foliation. So for instance, here. So this geodesic, they never intersect one to each other. So I have a slice on the left and I have geodesic flowing from them. So I can really write the volume measure here by disintegrating it in terms of this geodesic coordinate. If I do this, I will get a determinant, of course, of some Jacobi. It's a Jacobian. And it's not very hard to check that this A, of course, depends on eta. So you will get the t correspond to the integration along the geodesic, and eta is the parametrization. Eta, if you want, is the parametrization on the slice, on the set of giving you the set of geodesic. And this A of eta is going to be a matrix solution of the Jacobi equation. So it solves the Jacobi ODE, dt square A of eta plus R of eta A eta, and R of eta is the curvature tensor contracted with the geodesic, the tangent vector to the geodesic. And it's viewed as an endomorphism, so it's really an ODE. So using what we know about our geodesic flow and the fact that we have the same scattering map, we can show that A of eta, when t go to when t go to minus infinity, A of eta is going to approach the identity. When we look in the future, it's not going to approach the identity, but it's going to approach a constant matrix depending on eta, which is in SON. So with determinant 1. And moreover, when eta is large, which means you take geodesic on the cylinder, which go very far near infinity, H of eta is going to be close to the identity. So now there is a full set of kind of trick, which go back actually to some work of Berger. This is the way Berger proved the Blaschke conjecture on the sphere. So it's pretty nice to have to use a result of my grand mathematical father. And this is detailed in the book of Bess. And it's based on convexity property of the map, which to a symmetric matrix X associate the determinant of X to the power -1/2. It turned out that this map is strictly convex. So if you play with this convexity and Hölder or Jensen inequality, really very much like in the proof of the Blaschke conjecture by Berger. I don't really want to enter detail because it's quite technical. But basically, the idea is that the Euclidean, if you take A, for the Euclidean case, A will be 1. It will be the identity. And you have to play with this convexity argument and Hölder inequality. And what you can show is that you'll get an inequality, and the equality hold only when determinant of A is 1 and when A is the identity. And this kind of limiting case, it's exactly the case of Euclidean space. So it's a sort of convexity. You show that you have an inequality, and if there is equality, then A has to be identity, using this kind of proof à la Berger. So using this, we can actually show that if G is asymptotically Euclidean to order M strictly bigger than the dimension +1, and assuming that it has no conjugate point, then the matrix A of eta, using this kind of trick with equality case of Hölder and this strict convexity, is going to be equal to identity. And then, of course, if A is equal to the identity, when you come back to the equation that A satisfies, you see that R times A is 0, which means that the curvature tensor R is 0. And then you have proven that the curvature tensor is 0. So what we have proved now is that if we have a metric which decays fast enough near infinity, where the speed of decay is given by the dimension +1, then it must have 0 curvature. And why the dimension is coming in the asymptotic in the difference between G and the flat metric and the Euclidean metric, it's because of this estimate, this volume estimate here between f of R and f of R0. So you see that using this convexity argument and Hölder, we will get an inequality. And we want to show that we are in the case of equality in this Hölder inequality to be able to say that A is identity. And for this, we need to know that the volume between f of R and f of R0 is actually going to 0 and R is going to infinity. which is why we need M to be strictly bigger than N, the dimension plus 1. So now the last step of the proof, which is then completely different from Croc or Berger's argument, is to prove that if you have an asymptotically Euclidean metric to order M larger or equal to 3, if you assume that you have the same scattering map as the Euclidean metric, then in fact, G is asymptotically Euclidean to all order. It means that really the asymptotic expansion of the metric near infinity, if you write it in the good radial coordinate, has to be the same as Euclidean space. So for this part is really quite tricky. One has to analyze the geodesics very close, which are very far near infinity, very close to the boundary at infinity. So the idea is as follows. I don't want to enter detail because it's really quite technical. And there is similarities to some work of Joshi and Sabareto in quantum scattering, in inverse quantum scattering. But it's a bit different though, because we don't really have the same information as in inverse quantum scattering. Here we just have the scattering map. We don't have the amplitude. In the quantum scattering, you really have the classical scattering map, but also the amplitude. So the idea is to look at the geodesic equation in radial coordinates. So using this rho and theta or rho and y coordinate near infinity. So remember rho is 1 over modulus of x basically, or something like this, but adapted to the metric G. And if you write the covectors in radial coordinates, so xi0 times dr or minus dr, which is just d rho over rho square, plus eta sum of eta I dyi, where y are coordinate on the sphere. In fact, one can check that the geodesic staying in rho less than epsilon, which means in r bigger than 1 over epsilon, so very far near infinity, they look at first order. I mean, we can describe them under the form I wrote. It's a bit like the geodesic on a cone. So it's sin of s, cos of s, and then the Hamilton flow on the sphere for time between 0 and pi. So this appeared in the work of Melrose, for instance, in scattering theory for the class of manifold he was working on in the middle of the 80s, also with Maciek-Złorsky. So this is really the Euclidean case somehow. In our case, what we can see is that the geodesic look like this at first order, but then there is perturbation because we are not in the Euclidean case. So what one has to do is we expand the metric. We assume that G is G0 plus rho to the n minus 2 times some symmetric 2 tensor on the sphere plus lower the term. And we have to linearize basically the equation that the scattering map of G is equal to the scattering map of G0. And when we linearize, we reduce to some attenuated ray transform of the tensor HM. And so it's not really the ray transform, it's not really the radon transform on the sphere, but it's an attenuated version. And the weight in the attenuation, they are given by basically to polynomials. And in the end, I don't enter detail, but in the end, what is quite funny or interesting is that finally the result reduced to a result on the analysis of the kernel or ejectivity, if you want, of the X-ray transform on symmetric 3 tensors on the canonical spheres. And this was analyzed by Esteze in the 80s, or Goldschmidt, or Maciek-Złorsky. Maybe I should stop.
Thank you very much. Thank you very much, Colin. Are there any questions or comments?
Hello, can I ask a question, please?
Yes.
Yes, so your metric J0 is the Euclidean metric, as far as I understand, but can you consider more general metric J0 than the Euclidean one in your approach?
Well, I mean, we have another paper where we did this, but I mean, at least for what concerns conjugate point, it really makes sense to compare to the Euclidean one.
Okay.
Of course, I mean, you could ask the question if you have two asymptotically Euclidean metric, and you assume they have the same scattering map without assuming they have no conjugate point. what can you say about them? So for instance, our proof probably would, I think we did something like this maybe with Leo in another paper, would prove that the asymptotic structure at infinity would be the same. But proving a global result, of course, as you know, when you have conjugate point, it's always tricky. Even in the compact case, we know very little situation where this holds.
Okay, thank you.
Are there any other questions or comments? Please, are there any other questions or comments?
I have a question.
Please.
Huh, Steve?
Yeah. These proofs in the case of these cylinders or these asymptotically Euclidean things
Yes.
seem to be of a completely different nature from Burago and Ivanov's original proof in the case of a flat torus.
Yes.
Are any of his is more, you might say, more functional analytic or abstract, involving Banach norms and things? Is there any way in which those ideas can be used in this context?
You mean the ideas of Burago-Ivanov?
Yeah. He was using periodic metrics on the plane.
Yeah, yeah, exactly. Well, we actually, we tried a bit, but we are not quite successful. But I must say I'm not really familiar with Burago-Ivanov argument, but it might be possible. I mean, of course, their methods are a bit more flexible, so you could expect maybe a more general assumption, and that would be interesting. But at least in some of these this type of argument, so the periodicity is used. For instance, in the proof of Kroc, this volume estimate, it's very important, the fact that it's a universal cover of a closed manifold.
Yeah, the Burago-Ivanov argument's I don't remember it very well, but it's a very kind of beautiful, somewhat abstract functional analytic argument involving Gromov-Banach norms and things like that. At the very least, one would try to like figure out if there are any analogs of these tools in the asymptotically Euclidean setting.
Yeah, I think it would be interesting actually. We thought about doing it at some point. We tried a bit, but yeah, I think it might be worth. At least if it works, the nice thing is that it will probably give more general. I mean, the assumption would be with them. So I think you're right. It would be worth to try to check. But at least when some of the argument of that kind, I remember we're using periodicity. So for instance, we looked more at Kroc actually. But,
you mean the paper of Kroc and Kleiner that preceded the paper of Burago-Ivanov?
There is this one, and then there is another one for a universal cover of closed manifold. So I don't know. Yeah, it's a good question. At least it could be worth to really try to see what can be shown using their method.
Okay, thank you. Are there any other questions or comments?
Actually, this is Andresh. Can I ask a quick question, Colin? So the m greater than equal to 3 at the end of the day comes from this last part, the limitation.
Yes. Yeah. In this reduction near infinity, I don't know why, but when m equal 2, there is another messy term that is really annoying. I must say we didn't try extremely hard, but we tried a bit, and already it was quite painful to do the case m bigger or equal to 3. So we didn't want the paper to be extremely long. But yeah, it's a good question. I don't know.
It's very nice that in any case that the symmetric 3 tensor X-ray transform shows up somewhere.
Yeah, it's bizarre, I must say, but at some point there is the symmetric derivative of H of this tensor HM that comes, and you have some rate transform of this which come. Yeah, the proof is really, in the end, it's quite tricky actually. I was thinking it would be much easier, but which is maybe why, I don't know, maybe Steve's suggestion might be good in some sense, because here we're really having technical trouble, and maybe a more geometric approach could be useful for more, if we want to see what's the best assumption for this type of result.
Thank you very much. Are there any other comments or questions? Okay, if not, thank you very much, Colin. Thank you very much. Thank you very much, everyone, for coming. Thank you.
Thank you.